now bring to the stage Christian Posta. Christian Posta is VP Global Field CTO at Solo.io. He's well known for the cloud native community for being an author, blogger, speaker, and contributor to various open source projects in the service mesh and cloud native system. His blog is blog.christianposta.com. Christian, thank you very much for being here. The stage is all yours.
Wonderful. Thank you so much for having me. Hopefully you can see me okay. I'm super excited for this for two reasons, really. One, CraftConf it's probably my favorite conference, and I'm a little sorry that I can't be there in person today. Hopefully next year. Don't tell the other conferences that this is my favorite. But and then number two, I'm going to be talking about a topic that I'm very passionate about, how services connect to each other and working with organizations to make that a reality in their environments, and then pushing the boundaries. So I'm fortunate to be working at a company, Solo.io, that focuses squarely on this problem, application networking. And we get to work with some of the most advanced and biggest scale and complex scenarios where we're solving these problems, and we have to push the boundaries on the technology. And service mesh is probably some, if you're in this space, you've probably heard of. eBPF is also another buzzword that people are talking about. So let's look at how the service mesh evolves and how eBPF can play a role or be part of that. So as I was introduced, my name is Christian Posta. My family is from Hungary. Of course, I would love to come back and be with you all at CraftConf next year. I recently published a book on Istio back in March from Manning, so it's Istio in Action. And if you reach out to me on, probably Twitter is the best way, DM or something, then I'll try to get you a copy of the book, hopefully sign it too. So definitely feel free to reach out. So what is service mesh and how can it evolve, and how does the eBPF fit into it? And we can't start going down this path without understanding where we are today. So a service mesh is cloud native infrastructure or technology that solves the problem of how does service A talk to service B when there are policies that need to be enforced by the organization. And instead of doing it in the application code itself, how can we externalize it and apply it consistently to any application written in any language with any framework? Some of the policies that crop up, security policies. So is service A allowed to talk to service B? Is there context specific to when service A may be allowed to talk to service B? Or there are resilience policies, like if service B is going not well and is returning bad responses, then stop calling service B for a certain period of time. Or rate limiting or quota usage type policy. So typically these are built into the application or the code itself, or in the past, we've tried to funnel all of the traffic as much as we could through some centralized thing, whether that's an API management system or enterprise service bus or some centralized middleware. But this approach has always created challenges, both from a scalability standpoint, as well as from a process standpoint. How does team A influence the behavior of these policies and the implementation of these policies if it doesn't have control over them? If it has to go to some other team, open up tickets, Jira tickets, ServiceNow tickets, whatever, and then wait to have any of these changes take effect. Right. So the centralized middleware force everything through this centralized choke point. This doesn't work very well in a cloud environment, and it doesn't work very well for those organizations that are trying to enable self-service and move faster. So this is where the service mesh comes into the picture. With the service mesh approach, we assign proxies to handle this networking policy and this networking behavior on behalf of the application, and we assign them to the application. We basically say, here's a little proxy for team A and service A, run these things together. Now, when service A talks out to the rest of the network, that traffic always goes through the proxy, and now we have an enforcement point for applying policies like circuit breaking, traffic routing, initiating mutual TLS, collecting telemetry and observability. These are all very important aspects of what the service mesh brings, and the proxy is what delivers these capabilities. Right. So again, just recapping that the service mesh is in cloud native infrastructure that is implemented typically with proxies working with and on behalf of particular workloads that provide things like observability, traffic encryption, and security policy enforcement. All right. But how did this start? So if we ended up with sidecars and these little service proxies, how did this all start? Actually, this started a little while ago. This started, you can think with the Linkerd project, which originally came out. Linkerd folks actually took one of those libraries that people were using and embedding inside of their services and said, well, why don't we just take that library and we'll wrap it up into a container, and we'll have all of the workloads that want to talk over the network talk to this container. And what we implement inside this application library that's stuffed into this container will implement things like retries and circuit breaking and initiating mutual TLS and the service mesh like capabilities that were once in the application. Let's just pull it out and put it into the standalone thing. Right. And this worked out pretty nicely. It was very easy to get started. You just forced, you told your applications to talk through this forwarding proxy. However, there were challenges that cropped up in an environment like this, right? And they're not unique to service mesh. They're the types of challenges that you would see when you try to share infrastructure, especially across multiple applications. So you have one application that's doing something, maybe making a lot of connections. Maybe you have another application that's doing something different, maybe processing messages that are really, really big. And you start to get this tension in the middleware, in these shared proxies that compete for resources, cause issues for other services. If that proxy goes down, it affects everything. From a security standpoint, that proxy has to assume the identity for all of the workloads. So if that gets compromised, now you're in a situation you probably don't want to be, where one thing can pretend to be everything else, and so on. So these are issues that we ran into in the service mesh community from very early days. So now if we take a little bit closer look at what we've done to kind of mitigate and alleviate some of those issues, because we want the capabilities of the service mesh, but we constantly want to try to improve our security posture, our performance, our tenancy, how we solve for tenancy. And that's how we got to the sidecar. We basically said, let's take that proxy, maybe make it a little bit more efficient. The original Linkerd proxy was written in Scala and the JVM. Why don't we, let's make that a little bit more efficient. Proxies like Envoy proxy started to come to open source, and it became clear that Envoy could play this role very nicely. And let's put that proxy with the application instance on behalf of the application. Now we alleviate concerns around tenancy, because we're not trying to share a single proxy with a lot of different other applications, right? where we have a proxy per application instance even. We get that fine-grained identity and identity enforcement because we can assign the identity directly to the instance and not try to share some common infrastructure that assumes all of the identities. Right? So now we can write very fine-grained access policies. This service, not only this service, but this service living in this environment at this time of the day and so on, with this identity token and this JOT and so on. This, we can write very fine-grained policies about the service communication in an environment like this. And so as we compare it to the shared node model, we can cross service boundaries, cross node boundaries, cross cluster boundaries, and the call is going from service A to another service, and we can apply and enforce the networking policies, the access policies, quota policies, and so on at the level of these application instances. Now, that doesn't mean there aren't challenges with this approach as well. And those of you that have been running a service mesh at any appreciable scale will know this, and especially when you're trying to maintain day two and life cycle and so on. All right, so the first is when you start adding all these proxies everywhere, this is going to increase your operational complexity. All right, now you need a control plane. You need something to manage. This, service mesh usually provides this particular aspect of control plane. But you have to be aware that there is a proxy running on every service. You have to figure out how to correctly introduce the proxy so that it doesn't take down the service. There's some edge cases here where that can happen. You have to figure out how to upgrade that service. And that takes a little bit of planning. And then you also have to appreciate that certain environments, maybe like Kubernetes, weren't written with the idea of a sidecar process, and all of the edge cases that come along with it in mind. For example, in Kubernetes, you can run a job workload with a sidecar, but when the job finishes, the sidecar might still continue to run. So there's other things that you have to, there's more complexity involved here. The second is when you start placing these proxies in with all of your applications, there's going to be some amount of resource overhead and increased cost, not just in theoretical, there's some latency and throughput changes here, but actual money. Like when you're running these proxies, they take CPU. They take a lot of CPU at times. They take memory. They need to store a lot of their configuration and grab telemetry and a lot of the health checking that is involved in making sure that these are operating correctly. So there are drawbacks to this approach. Now, when we work with our customers at Solo, and we can say that we're working with some of the largest deployments of Istio, some of the largest deployments of service mesh in the world, from a few hundred clusters to thousands or tens of thousands of clusters deployed geographically, distributed, hundreds and hundreds of data centers, all 4 public clouds and so on. So we do see some customers are very interested in how do we optimize away some of the downsides of running a service mesh like this. But I would say a majority of them, they appreciate this sidecar model, the tendency that they're able to achieve with this model. However, like I said, there are these challenges, and we should continue to try to optimize and improve them. And here's where things like eBPF might start to come in. Some of these newer technologies, maybe trying to figure out how this might work a little bit better with the CNI. And our friends at Isovalent published a blog not too long ago that definitely caught our eye. This is definitely something that we've been looking at and working on with our customers, especially with something like eBPF. And I'll explain what eBPF is in a second. But one of the things that they pointed to and started talking about was, you know, how do we get rid of the sidecars so that we can improve, drive down costs and improve operational complexity and start solving some of these problems. But they kind of wrap that all up with, well, if we get rid of the sidecars, eBPF can replace the sidecars, and there were some things in there that would be worth clearing up here in this talk, especially. The first thing that they propose is, while they try to optimize everything into the kernel using eBPF, that we should start with the shared proxy approach, and that's what they're prototyping. Now, if this looks similar to what we tried and started to do in the early days of Service Mesh, you would be correct to see that. That is exactly the direction that they're talking about going. Along with, well, why don't we just rewrite the proxy, put everything into eBPF and stuff it into the kernel? And so that's where, we've talked about this. Running shared proxies in an environment like this has, challenges with multi-tenancy, especially at the application layer. These applications are built and tuned to provide whatever service, whatever API they're supposed to do. But if you try sharing that is going to conflict with the other services that need to run and share with that proxy. Our customers, when you get to a certain scale, and maybe it's not even a scale, maybe it's just a real enterprise environment where they already have legacy software, they already have established security protocols, that you can't just introduce a new piece of networking technology and all of that stuff goes away. You have to play nicely in that environment. So being able to extend the capabilities of the data plane, whether that's directly extending Envoy, using WebAssembly, using callouts, whatever it is, those things can directly impact and affect how you share infrastructure like this. So extensibility is a big key. And then we talked about some of these things that we already saw in early days of Service Mesh, where giving a single shared infrastructure the right to impersonate every other node or every other workload, that can be dangerous if it gets compromised. And a lot of what we see in the CVEs that crop up in these types of proxies, they show up in the area of layer 7 of the application layer. That's where it's it's certainly very possible to trick the proxies into different vulnerabilities at this layer that provide even more reason to kind of lock it down and avoid some of these tenancy issues if we can. To the extent that the folks that wrote and worked on Linkerd from the very beginning noticed this, and correctly, I think, called it out that, hey, we're going backwards a little bit here. That eBPF is an exciting technology, but we can't hand wave over here and regress over here, right? So where does eBPF fit? And can it help push the boundaries of the service mesh in the right direction? We believe so. But first, what is eBPF? So eBPF is a way to extend the capabilities of the Linux kernel in a dynamic way and a safe way. All right, so we can write little packet filtering scripts that can be verified by the kernel to not crash the kernel, because you probably are aware that the kernel is a pretty important part of cloud native infrastructure, and then execute that with a known stopping point and expectation of safety, and then, can continue operating. And if you've used things like TCP dump or net filter, these types of things, these are implemented with this type of logic. Now, specifically, what we do with eBPF is we write these little programs, and we attach them to hooks and various events that can happen in the Linux kernel. You can think of it almost as a functions as a service, if you're familiar with that term, but for the kernel, right? With the same sort of idea about the limitations that might be imposed in an environment like this, where your code can't run infinitely. It can't allocate memory and do all of these fancy things that you would expect in maybe a more full featured or Turing complete type language or instruction capability. And you don't get to decide when it gets invoked. The kernel will decide. So if there are packets flowing in through the network, either on the network stack or coming to a device or whatever, you can instrument or inject this custom code into that into the kernel and have that run at a particular point. And so this is extremely powerful, especially in the terms of networking, which is where service mesh and this type of conversation comes up. So because eBPF can run at this low level, there are things that it is well suited for, and because of its low level and the constraints in which it has to run, eBPF is well suited for certain things and not well suited for other things. All right, so as packets are coming in, can we evaluate them and redirect them? Can we do things like maybe bypass certain parts of the networking stack? Maybe we can do some simple load balancing or redirection, or we can maybe do some very light parsing so we can understand what is happening on the network. Maybe collect more telemetry. Those are really good use cases for eBPF. eBPF is not as well suited for some of the complexities that we see in handling layer 7. And layer 7, that's where the requests are flowing. That's where HTTP1, HTTP2, HTTP3, those protocols are implemented. And so the idea that we can just replace a proxy with eBPF, at least today, is not a really a viable approach. What we've found is trying to implement complex things that require complex state management and more complex data structures, things like handling stateful load balancing, things like handling JOT tokens and claim-based routing, and maybe calling out to external auth type services, even resiliency like circuit breaking or retries, right? If you think about what has to happen in the event of a retry, first we have to send the request. We need to wait for its response. We have to evaluate, what is this response? Do I need to retry? If I retry, I need to schedule maybe some exponential backoff. And then I need to call again. I need to continue, I have to halt being able to respond to the original caller. I need to somehow allow the stream to continue because I don't want to do head of line blocking and block everything else from proceeding. Retrying is pretty complex, and doing this without more freedom in the Linux kernel with eBPF is that it gets extremely complex, extremely difficult, and is probably not the right place for us to implement this type of functionality. As we'll see, a lot of the complexity and a lot of the overhead in handling these types of capabilities that a service mesh needs is very CPU intensive, right? And doing it in eBPF doesn't really save you from those CPU cycles. In fact, it's probably a lot more complex. So if there are good places to run and use eBPF, and then maybe there are not so good places to run and use eBPF, let's talk about where it can be helpful and be useful. So the first is in the areas of networking around the proxy, around in the case of Istio, the sidecar proxy, which is Envoy, and how that traffic flows through the network, right? And so in the Istio case, we inject the sidecar proxy, we transparently try to route traffic so that when the pod talks to the outside network, it's forced through this the service proxy. So let's take a look. Let's say the sleep pod is trying to talk to some service on this port, some port, doesn't matter. What we'll use is IP tables to grab that traffic, grab those packets, and redirect them and force them to the proxy, and we'll force it to the proxy on a particular port. In Envoy, in Istio, the way Istio is configured, if it arrives on a particular port, it knows that, hey, this traffic came from the application, is destined for the outside world somewhere, and to treat it as though we know it was automatically redirected by IP tables. And then Envoy is configured to do matching on the request and figure out exactly how and where it needs to be shipped. But IP tables is used for the redirection here, and it sends it to the local host on a particular port where Envoy is listening. Now, as mentioned, eBPF can be attached to certain points in the kernel, and some of those points along the networking stack, so that we, as packets are flowing, we can intercept them and redirect them without having to go through IP tables and all this stuff. We can have much more fine-grained programmatic control over how that redirection happens. Now, there are certain capabilities in eBPF that allow us to directly put the data from one socket into another socket without having to traverse the networking stack. And so that's what we can do. That's certainly one thing we can do to accelerate improve the latency and improve the throughput of traffic between the workloads and the sidecars themselves. And so in this case, the sidecar is trying to talk to the outside world, the network, and we're going to use eBPF to force those packets directly to the proxy, bypassing IP tables, bypassing the networking stack, and saving that altogether. And in our testing, we're using the Istio performance testing benchmarks. We enable or disable our eBPF acceleration, and we're sending 1,000 requests per second. We can see that with eBPF enabled, we do have a bit better performance here in terms of latency. We also saw improvements in throughput as well. And then here's that was at P50. Here's at P99. We still continue to see observable improvements in the latency profiles. Now you can think, well, this is kind of minimal, and it is, but aggregated across a large fleet or a large set of workloads, this can be a performance optimization that you can gain without really having to do anything. At Solo specifically, we've enabled this for our glue mesh product, which is built on Istio, that you hit a flag and you get this saving automatically. Another area that we talked about is how the service mesh enables a level of observability and telemetry collection that eBPF can certainly help with. In a service mesh like Istio, as the traffic's flowing through the proxy, we can get a lot of information about what's happening. Things like how many requests are flowing, or how long those requests are taking, or how many retries or circuit breaking events that we're seeing, or errors that we might be seeing. And we can capture that in using Prometheus or some telemetry collection tool and export that to things like Grafana and build nice dashboards. And what we've seen in practice is these dashboards are extremely important and extremely useful in helping to troubleshoot and diagnose problems when they occur in the network between the services. We can also draw nice diagrams, and we can get a better visual understanding of what's happening with the traffic in our environment. We can get this same visualization when things start to go wrong. But there are gaps in this, just as we mentioned. It's not a panacea with the sidecar approach, because what happens with those workloads that are not injected with the sidecar? What happens to those metrics that the Istio proxy or Envoy can't or shouldn't try to keep track of because of the cardinality explosion problems? And having additional telemetry about what's happening in the environment to merge or to align and complement what's happening on the network would also be very, very, very helpful. And so that's where things like eBPF can come in and fill some of those gaps, right? So we can have the proxy, have the workloads themselves, they're exporting their metrics, but we can also include the telemetry that's coming from the infrastructure, from the lower layers of the network, and even maybe offload some things like tracing that might otherwise be kind of expensive to do in the application or in the proxy itself. So eBPF at these layers for acceleration, for observability, can bring massive operational improvements and kind of push the direction of the service mesh in the right way. The last bit is going to be about how eBPF, or having control over those lower level network packet flows, how that can be used to improve the placement of the proxy. Right. So we did talk about the here, so just come over here real quick we did talk about some of the pros and cons of the sidecar model, where you get good tenancy, where you get not so good resource overhead and resource usage. And for those folks who care more about being backward compatibility with your applications, about the various features that you can use and offload away from the applications, what we've seen is this is not the resource overhead and performance isn't that big of a consideration right now. But we also have those customers that are dealing with much larger environments, and this sort of cost optimization is top of mind. And we talked about some of the advantages or disadvantages of the shared proxy per node model, where you have the proxy that is shared across all the workloads on a particular node. You can use the redirection logic and use eBPF to control the packet flow between the workloads so that they always go to the proxy, and then you get better things like better resource overhead and so on, operational overhead and so on. But you lose things like feature isolation, like your security granularity, and there's trade-offs to both of these approaches. Now, those are not the only approaches. There are sweet spots where we can trade off. Maybe doing a service account proxy where you're not trying to share the proxy across multiple different tenants, but rather you have a proxy per service type or workload type. And then use things like eBPF, use whatever lower level networking that you need to force the traffic from certain workloads to the appropriate proxy that handles the workload for that environment. And then you start to kind of move around some of the trade-offs that you're willing to take. And so this is something, these types of improvements in acceleration, in observability, and in proxy placement, including moving the proxy completely off of the node and putting it somewhere else. These are all things that we've been working on at Solo with our distribution. We wrote a blog about this back in December that goes into some of the detail here, and so we feel like this is the direction that that the service mesh is going, where eBPF can help, where it can't help, and we're working with hand in hand with some of these really large deployments and our customers that are deploying service mesh at scale. I think I'm running a little bit short on time, but what I will say is, here, let me try this. Let me just finish up. So like I said, this is what we're working on at Solo. We're a application networking company that we incorporate modern API gateways, the service mesh, and the CNI layers all into a cohesive, consistent, and enterprise supported stack. Istio is a big part of what we're doing at the service mesh and gateway layers. Cilium is a big part of what we're doing at the CNI layer. And bringing these things together is where we see the service mesh going. Feel free to please reach out and check out some of these events. We do a lot of education, both live and on demand, around these areas of the technology stack. We are absolutely hiring for just about every position you can think of. We're a very remote friendly company, extremely good culture here. And you'll definitely be impressed with the rate of speed that we're able to move, and the the amount of learning that you'll be able to do here at Solo. But let me just say thank you so much, CraftConf organizers, for having me. Really wish to be in person. Hopefully we can make that happen next year. I leave my contact information for the attendees. Please feel free to reach out. I will, like I said, I'm running a little bit short on time here. Want to take a couple questions if we can, but I will post some demos here, and I'll probably publish them on Twitter and LinkedIn for y'all to see. But that's the end of my talk. I appreciate it again. Thanks for joining.
Thank you very much, Christian. As far as I can see on Slido, we don't have any questions, but if anyone wants to have a question, just please shoot it now, or then afterwards, just send it directly to Christian. I'll give it 1, 2, 3. Yeah. Sorry, Christian, we don't have any questions right now, but I'm sure that people will reach out to you on your Twitter or email.